Hey everyone, and welcome to this explainer, proudly brought to you by Forge College. Today we are pulling out the engineering blueprints to tackle one of the absolutely most critical security differences in all of Web3. We're talking about permissions and access patterns, specifically what holds up and what completely changes when you transition from the Ethereum virtual machine, the EVM, over to the Solana virtual machine, or SVM. You can think of this as the master key to your whole security mindset shift. As we map this out today, we're going to see exactly how these permission models translate, or in a lot of cases, completely fail to translate across these two environments.
So, let's kick things off with a million-dollar question. Why does copy-pasting your Ethereum permissions directly over to Solana usually end in a total disaster? I know, it sounds a bit dramatic, but it's just the reality of the landscape. Remember in our last lesson, we dug into numerical and reentrancy behaviors, right? Well, here is the kicker. Permission checks are the actual guardrails that stop those bugs from ever being triggered in the first place. If you breach the permission guardrails we're talking about today, boom, those numerical and reentrancy bugs become wide-open exploits. Copy-pasting assumes the underlying architecture is exactly the same. Spoiler alert, it's not. And making that assumption is basically how you leave your digital front door wide open.
All right, here's our game plan for today. First, we'll look at EVM versus SVM ownership. Then, we'll compare roles versus capabilities. Third, we'll check out cross-program boundaries. And finally, we'll wrap up with the actual code clash and some key takeaways.
Part 1, EVM versus SVM ownership. Basically, where does authority actually live? Let's start with what you're probably already super familiar with, the EVM. I like to call this the fortress model. In the EVM, ownership is usually locked down by an owner variable. This is just an internal contract storage variable that holds a specific address. So when someone tries to execute a privileged function, the contract checks that stored address against the immediate caller, msg.sender. It's like the contract is acting as a bouncer at a super exclusive nightclub. It's holding its own internal VIP list. Someone walks up, the bouncer checks their ID against that specific list and decides right then and there if they are getting in. The permission logic literally travels natively inside the code itself. Now, contrast that with the SVM. This operates much more like a toll booth model. In Solana, programs hold absolutely no state. They are just stateless executable code. So instead of an internal VIP list, we have the signer flag. This is a transaction-level Boolean, just a simple true or false, that tells us if a signature was provided. And this is checked against completely separate, stateless data containers that we call accounts. The program itself? It has zero memory of who the owner is. Users literally have to drive up to the toll booth, hand over their own ID in the form of an account, and provide a signed permission slip.
Looking at this blueprint side by side, the differences are pretty stark. Check out the authority row. The EVM relies on internal storage and msg.sender, whereas the SVM relies on external keys and those signer flags. Now look at the check location. In the EVM, you are doing the check inside the contract code right before you mutate the state. But in the SVM, you have to verify this right at the program entry by validating the account metadata that comes with the transaction. And for delegation, EVM uses internal role variables, while SVM requires you to physically pass accounts or program-derived addresses. The absolutely crucial takeaway here is that EVM permissions travel with the code, but SVM permissions require you, the developer, to explicitly verify that transaction metadata every single time. Moving on to Section 2, Roles versus Capabilities. This is how system access patterns actually play out.
In the EVM, we rely heavily on role-based access control, or RBAC. This basically means we are centralizing lists of admins right inside the contract state, usually using mappings. You just map an address to a Boolean, true if they aren't an admin, false if they aren't. It's that centralized VIP list all over again. But think back to our previous lessons on reentrancy. If a privileged function makes an external call before updating this centralized state, an attacker can absolutely exploit that transient state. Because RBAC in the EVM is so centralized, your exact order of operations is absolutely critical. The SVM, on the flip side, is a perfect fit for capability-based access. Instead of putting someone on a central list, you grant rights by passing specific account references and signer flags. It's kind of like handing someone a physical cryptographic keycard. You pass the account proves it has the signature, and boom, the rights are granted based on that capability right in the moment. It moves authority through the simple passing of verified accounts rather than querying a centralized database. It is a totally different mental model.
Okay, Section 3, Cross-Program Boundaries, because trust is definitely not implicit out here.
So the single most important point here is this. Trust is never implicit across boundaries. On the EVM, a call implicitly carries the authorizing key along with it. But on the SVM, if your program calls another program and expects that callee to enforce an admin check, you absolutely must make sure the callee requires a signer and validates the correct account. If you just toss an account over the boundary without strict validation, the receiving program might just assume everything is totally fine. I mean, you wouldn't hand a total stranger the keys to your house, right? You have to explicitly enforce trust at every single border crossing.
This difference really shines when we look at multisig architectures. On the EVM, a multisig is this explicit, contract-level logic designed to collect and aggregate signatures on-chain. But on the SVM, multisig is a transaction-level check of multiple signer accounts, or threshold stewards. As an SVM developer, you have to manually validate account order and public keys. You absolutely cannot just assume the runtime magically fed you the correct accounts in the right order. If your validation is lazy, an attacker could just slip in an alternate account at the same index and completely hijack your multisig.
I have to stop and share a massive warning here, because we have seen real, catastrophic incidents of this in the wild. Checking an account balance is absolutely not a permission check. We have literally seen developers accept an account just because it holds the expected Lamport balance, the native token on Solana, instead of actually checking its identity and signer status. Guys, that's like a bank vault letting someone waltz in just because they have a $5 bill in their pocket. Having the right balance means nothing. You have to verify their cryptographic identity and make sure that signer flag is explicitly set.
Let's move to Section 4, Code Clash and Takeaways. This is what moving logic to the SVM actually looks like. Take a look at this code comparison. On the left, you've got a standard EVM owner-only modifier in Solidity. It implicitly trusts the require msg.sender equals owner check. It's co-located directly with the state mutation. Super simple. But on the right, we have Rust using the anchor framework for Solana. You would typically use the account signer macro, but, and this is a massive critical pitfall, anchor signer macro does not automatically verify the identity of the signer. It only verifies that a signature is present. If you just drop in that signer macro without also explicitly comparing the public key of that account to your stored authority key, literally anyone who signs the transaction can authorize the action. Seriously, no joke. Anyone? So, to make sure you don't accidentally leave your front door wide open, here is your vital porting checklist for moving owner-based logic to the SVM. Number 1, never assume signer presence equals an identity match. Number 2, always explicitly compare public keys in your code. Number 3, validate your program-derived address, or PDA, derivations whenever they act as authority holders. And number 4, confirm your account mutability constraints. Basically, make sure an account is marked as mutable only if it actually needs to be.
Look, if you only take away one single thing from this entire explainer today, let it be this. Burn this security rule of thumb into your brain. Signer presence does not equal identity match. Just because someone signed the guest book doesn't mean they actually own the house, right? You always have to check their ID against the deed.
And that brings us to the end of our blueprint for today. By mastering these foundational differences in permission patterns, you are now fully equipped to spot where vulnerabilities actually hide. Up next, we'll be teasing apart program-derived addresses and doing a deep dive into an overview of SVM-specific attack surfaces. Before you write your next line of code, really ask yourself, are you accidentally leaving your Solana front door wide open just because you're still thinking in Ethereum? Remember, this explainer was proudly made by Forge College. To dive deeper into this subject and continue leveling up your Web3 security education, definitely go check out forge.college. Keep building securely, and I'll catch you in the next explainer.